Okay, 4.13, right triangles, slopes, and lines. In this video, we're going to talk about how we can use a line to act as our hypotenuse of a right triangle. We've talked a little bit about right triangles and their hypotenuses when we talked about the Pythagorean theorem. Remember that right triangles are any triangles that have a 90-degree angle, and our hypotenuse is going to be this diagonal line. Remember, we referred to it as C when we were dealing with the Pythagorean theorem. So what we're going to be doing today is we're going to be taking lines that you graph, and since we know that it has a constant rate of change, we're going to be making these into right triangles. Okay, and you're hopefully going to be able to see that the right triangles can be all different shapes and sizes. Okay, but what they're going to have in common is that the line that's going to be graphed is going to form their hypotenuse. Then by counting spaces on our graph, we should be able to get the measurements of each side and yeah, use our slope and compare that to slope and our rates of change. So diving right in. Our first video note. As you can see, we have a line here graphed, and we're going to try to make two triangles here. The first triangle, I want to kind of do it for you, and I want to show you that if we connect these lines here, we really have a triangle, and that is a right triangle because it forms that 90-degree angle. Okay, because it forms that 90-degree angle, we're going to now use our side lengths to find our slope. As you can see, going across the bottom here, this is going to be 1. And then how many spaces up are we going? 3. So this right triangle is 1 space, the base of it is 1, and it's got a height of 3. Okay? Its hypotenuse, we don't really need to know that length, but what we're trying to see today is that this right triangle shares a similarity between our line. This hypotenuse is going to be part of the line that's graphed. As you can see, the sides of this right triangle then also act as our slope. So we're going to call this triangle 1. Okay, I'll circle triangle 1 in green so that you can know that the green triangle is our triangle 1. And our rise in this one, our vertical increase going up and down is 3. Our run is 1, or our horizontal base is 1, so our slope of triangle 1 then is 3. If we look at triangle 2, the other triangle we can draw is if I come all the way down here and then all the way over, we made another right triangle here in red, and that's going to be our triangle 2. Okay. Triangle 2 has 2 spaces for our base, and 1, 2, 3, 4, 5, 6 spaces for its height. So when we look at the vertical here, or a rise, we're rising 6 for this triangle. And our base is 2. So even though there's a different height and a different base for these two triangles, look what happens when we simplify that down. 6 divided by 2 is still 3. What we've shown here is that these right triangles still have the same slope, or we're using them to prove that the slope of this line is consistent no matter where we're at on the line. So if I erase everything that's in here, and I do our typical rise over run and pick 2 points, we can pick these 2 points. Our rise is going to go up 1, 2, 3, so our slope is up 3, and our run is going to be over 1, 1, so we get a slope of 3. The whole purpose of today is to be able to show that our right triangles are really, is really what we're creating when we make this slope. And that there are a lot of different right triangles that we can form. Let's look at one more example. I want you to go ahead and pause this, and I want you to draw 2 different right triangles. And let's see if you get the same ones that I get. Go ahead and pause it. Okay, hopefully you got these. These are the two right triangles that I got. If I draw my right angle here, got one there, and I can draw this one as well. And we'll call triangle 1 or red one again, and triangle 2 will be our blue one. Okay, I'm trying to find the rises and runs of each one of these. Let's start with our red one. Our red one, we're going to have a vertical increase of 2, so that means our rise is going to be 2. And we're going to have a horizontal increase of 1, so our run will be 1. 2 divided by 1 gives us 2. Looking at the blue, our vertical is going to be 1, 2, 3, 4, 5, 6, 7, 8. So 8. And our horizontal will be 1, 2, 3, 4. And looky here, 8 divided by 4 still gives us 2. Now, instead of using the rise over run method to prove that these slopes are the same here, I'm going to go ahead and use our y2 minus y1, x2 minus x1 formula. We have 2 points here, and so if we just use any of these 2 points, we can use this one and this one. Okay, we will call this x1, y1, and this x2, y2. And if we do this correctly, we should get a slope of 2. So our y2 is negative 4 minus our y1 is 2. All of that will be over our x2, which is 1, minus our x1, which is negative 2. Negative 4 minus 2 gives us negative 6 over 1 minus negative 2, well, that's the same as plus, so 3. We should get negative 2. So this is a really important thing that we just discovered. Because it's negative, we need to be careful. Our slopes over here should be negative as well. What I forgot to mention is that because our vertical increase is going down, we know that that's in a negative direction. So both of our negative 2 and negative 8 should have been negative here and here. So go ahead and make those corrections. I'm glad we double-checked it using the slope formula, because this is definitely a negative slope. Okay, that's everything I have for you today. Go ahead and proceed through the packet. Good luck.